So welcome everyone. So we are going now for our lesson 2 as far as circular motion is concerned. Yeah, hope I'm with physics students. So in the first lesson, we had a look at so many introductions, especially to do with the terminologies that are used in the topic. And for today, we are going to continue with more, basically two. And we also talk about other kinds of cases. Hope you understand. So if I'm to go back briefly to the book, you can see that the very first subtopic, that is the centripetal force. We tried to do some things. We had to cover that. We talked of angular velocity, angular displacement. We talked of linear speed. A lot of things in the first lesson. And for today, I want us to concentrate on angular acceleration, then the centripetal force. Of course, we are going to have derivations for both this and this, and then we are going to solve more problems. And then in these related numerical problems, we shall have some nice cases to do with the horizontal circle. Yeah, because there are some books that confuse the horizontal circle with the conical pendulum. Yes, they have a few things in common, but for now we are going to separate them. We are going to have the basic horizontal circle, then we shall look at the conical pendulum on its own. But still for today, we are going to have some conditions of the horizontal circle perfected, learned and understood. Hope you all are aware that for the case of the the vertical circle, it's not part of the syllabus. So we are not including it anywhere. So if you learned it, it was just good to know, but it wasn't a must. That's the plan for today. Angular acceleration, the centripetal force, of course, derivations, calculations with numerical problems that have different cases. And then we shall end it at that. The next time, we cover the conical pendulum. This one, we need one class. And then we shall end with these ones. Yeah. But remember, the remaining lessons of the week, we shall be covering waves. We shall introduce waves and then go into progressive waves. Hope you are aware. Okay, now to list my lesson targets very fast. Angular acceleration. We'll talk about the centripetal force, of course, under central forces. Then we shall see different calculations and etc. Of course, I always leave class with research and assignment. Yeah, that will be enough for today. That will be enough for today as we prepare for waves. Okay, now to begin with, you all know that when we are talking of velocity, I remember teaching you in linear motion the first lesson that acceleration alone is the rate of change of velocity. And as we are talking about velocity in our lesson 1 of circular motion, we talked of the linear speed, which is uniform or constant throughout the circular motion. Then we talked of the what? The angular velocity. And we also talked about it as the rate of change of what? Angular displacement. And you all know the angular displacement as that angle of course, displacement. So let me hope you remember those few terms that we discussed in lesson 1 because we are going to need them right now. And you should know that angular displacement is denoted by theta, angular velocity is denoted by omega, linear speed or linear velocity by small v. Because if you don't recall those, then it will be quite absurd. Then our radius is always r. We usually use our center as o, unless otherwise, things like that. Then our theta is always in radians. Our omega is always rad per second. Our linear speed of velocity is always meters per second. Hope you recall frequency and periodic time or the period and how you relate the two. How you can have our angular velocity in terms of revolutions per second, how period relates to frequency, and how the two relate to angular velocity. These are things you need to know so that as we calculate, we get to know the right formula to use. As simple as that. Okay, now, so have it in mind. I told you that you should be having the books you're using. So we are always here to make the points very clear so that when you go into your books, whichever books you've been using, so that you understand. So that when you look at how things are being brought up, you get the points. Okay, now, have our heading, centripetal acceleration. So centripetal acceleration of the body, that's what we are going to begin with. Now, you need to know that this alone, we know it as the rate of change of velocity. So that one you should appreciate. Rate of change of velocity. Then we all know, I don't know whether we have anyone. I don't recall us talking of the word centripetal in the beginning, but who can help us recall something about centripetal? Or who knows something? What can you say if at all they come out and say centripetal? What do you understand? What do you understand? I don't know if we talked about it, but to save time, let me help you. So by centripetal, in whatever we are going to be dealing with, have it in mind, it means towards the center. And we talked of the center in the beginning. So centripetal towards the center. So when we talk of acceleration alone, it's rate of change of what? Velocity. When I talk about centripetal, have it in mind that I'm meaning anything towards the center. So this acceleration is going to be towards what? The center. Of course, we are talking of circular motion. The center is something obvious. You get the point? Now, you all recall that whatever comes in circular motion should be in position to keep our body in the circular path. So when you find a book saying rate of change of velocity of a body moving in a circular path, it is the same. Provided anything is trying to help us and act towards the center, we shall keep in circular motion. And that is all. Yeah, hope you understand. Okay, so you can just add on and say towards the center of the circular path. So this is what I meant, that I may not write for you the definition of centripetal acceleration, but I've tried to break it down for you. So trust me when you read it, I've just said it, but I've not written. but when you read it, you'll understand. And if you've made a statement out of what I've said, you have the right definition. This is all to save time. I always just want us to derive and calculate, derive, calculate, derive, calculate. So now let's derive the formula of centripetal acceleration. So we need to first understand how it is denoted. Yeah, so we are going to first say it is denoted by that small letter a. So don't think it is so different from other accelerations. After all, it's not under gravity. So we don't what? Small a. As simple as that. We are going to use the same consideration as that we had before. Yes, Richie.
My concern is about that definition there. Is it the rate of change of the linear velocity over the angular velocity?
Oh, of course. Can you tell me the unit of acceleration?
They are meters per second squared.
They are meters per
Velocity,
second
they are
squared.
meters per
I want you to tell me, This one is what?
the
You
rate of
talk, you
change
talk.
of. I'm not
Okay.
getting you.
I was asking you the unit of velocity and that of acceleration. But let's look at the consideration as we derive. Then you see what exactly we mean. Because as of
Oh,
now, we have two formats of velocity. Let's do the consideration
oh,
and we see how everything is going to happen. Is it okay?
yeah.
Okay, now let's consider. So let's say that consider a body moving in a circular path. Consider a body moving in a circular path, of course, along the circumference of the circle. Of radius, we always use small r, and of course, center O. Yeah, so that you're aware what O is and what R is. The rest of the things we talked about them before. Yeah, the ones of the body moving from A to B. We're going to see everything. So let me first have my sketch. I told you that in case our circle doesn't come out perfectly, you pardon us, but it usually does. Hope you have tried. So we are going to have, of course, our center O. So please you listen to every statement made so that you don't get lost. Okay, so our center is O. Of course, remember we had our point A. Then we said that this body will be moving. Of course, if you recall, we said that our center is always the fixed point. And it's moving up to this point. Which was our point B, if you recall. So we had our line here. We had that one there like that. Then remember telling you about our angle, the angular displacement, which can be theta, or they can say small change in theta, which is delta theta. And then you all know that this is our radius r, our radius r. Then I remember telling you about the linear speed. Yes, the linear speed, the v, the one that is always a tangent to the circular motion. So I'll come and show it. So come and show it at this point, like that. Then also come at this point B and show it like that. So don't forget it's our v linear speed, it's our v linear velocity, any. And then you all know that it's always perpendicular. That's why we have those angles of 90. It's always perpendicular to our circular path. Okay, now when you look at the view we are having at point A, it's only having the horizontal component. So don't focus about its vertical component. It is purely horizontal. So this is the derivation. Hope you follow whatever I'm saying. Now, when you look at our V, the one at point B, it's of course at an angle to the horizontal. That means it's having the horizontal and the vertical components. You get this V, the one down, it's only and only having the horizontal component, no vertical component, because it is purely horizontal. But this one at point B, this is what I mean. No vertical component, only horizontal. Horizontal, yes, vertical it doesn't have. Then this V, it is at an angle with the horizontal. That means it has both the horizontal component and vertical component. So we are going to show them. These are things we've been doing. So you all know we shall have its vertical component. We shall have its horizontal component. But you all know I can shift this this vertical component this side. Thing that is known by everyone. So I can have my horizontal component. I make it stop somewhere here. Then I shift my horizontal component this side. Sorry, my vertical component this side. So when I shift it, hope you will get it. Now the problem will be about the angle, but you will understand. So I'm going to have the horizontal component the other side with the vertical component. Okay, so we said that here we are having our angle of 90. Then we are having the horizontal component here, and I can make it stop there. Then I also have my vertical component. And hope you all know that we also have there an angle of 90. Should be organized. So we are saying that horizontal component, that. Someone tell me which angle is here. It's not usually necessary to show it. You all know what we do for the horizontal component. You all know what we do for the vertical components. But which angle is there? Anyone who has an idea? Anyone with an idea? Okay, you people may be good physics students when I'm just wasting your time. This angle is the same as theta, the one there. Do I really need to show you how it comes about? Do you know why it's theta? I should show you. Because you don't need to just cram. But if at all you know the explanation well and good, because we come across these things so many times in physics and math. So I don't know, are people aware that that is theta, or I should show you? Okay, people are telling me to show. Okay. Okay, that means I'm supposed to handle you slowly. Because you refuse to do my assignment. So I don't know whether you're good physics students or you are hardworking physics students. But let me show you. Okay. We are having our circle like this, not so. We are having something like this. We are having here theta, not so. Then we are having this, isn't it? Then we are having here a triangle, isn't it? So you all know this is an angle of what? 90. Aren't you aware? So which angle are we looking for? This one. I can now first call it x, not so? Then if at all I make this straight line complete, are you seeing that? It will make this angle 90. I don't know if people are following. So after making it 90, this is the structure I'm coming up with. I'm coming up with this. I'm having this here, not so? I'm having this here. I'm having this here. Isn't it? What am I looking for? I'm looking for this x. Which angle is here? This angle here is 90. Which angle is here? This angle is theta. Which angle is here? This angle is 90. 90 degrees. 90 degrees. But I'm looking for this angle x. You get? So the very first thing I would do is first and foremost getting this angle. I'll first get that angle. And let me tell you what that angle is. So let's first get this one. Can people accept that theta plus 90 plus that first angle I want to get have a total of 180? Do people agree? I want us to go slowly. Yes, people agree. True. Can now people see that that angle will be 90 degrees minus theta? Do you see that? Because it will be 180 minus 90 to give us 90. Then theta goes the other side to get us this. So people, are we together here also? Okay, yes. Now, do you also realize angles on a straight line? When I get theta and add 90, so when I get our question mark and I add 90 degrees and also add the x I'm looking for, I'm also supposed to get 180 because those are angles on a straight line. Is this statement right? The first one was angles in a triangle. Then the next thing is now angles on a straight line. Question mark plus 90 plus x 180. The other one was angles in a triangle. Are we at the same page? True. Now let me now substitute. My question mark is 90 degrees minus theta. Only that. Then I have plus 90 plus x equaling to 100 and what? 8. Are you following? Then I proceed. Remember, I want x. 90 and 90, 180. Minus theta plus x equaling to 100 and what? 8. I don't know whether people see this one cancelling. This one cancels with that, isn't it? Then my x is theta. Do you see that? Do you see why our x is a theta finally? Should we now proceed with the physics? That has been bogus math. But we are interested in the physics. Okay. That is good. That means I can remove it. So you now know why it's theta. Now we are going to do with the resolving the horizontal and vertical components. Horizontal and vertical components. Okay, so we get back. We get back here. So the horizontal component, you all know. Remember, it is V. Our velocity at an angle is V. The horizontal component, you all know it will be V what? Cos theta. Hope people are aware. It's like forces. Those who attended with me projectile motion, you now know that these ones are obvious. Horizontal component, V cos theta. This one, V sin theta. Now we have the two. And that is the diagram we are going to use as we derive, nothing else. Nothing else. Remember, we are deriving the formula of what? Our centripetal acceleration. So that is the formula we are going to use. So the other words that we use, do you people know them? I can just try to write them chap so that people know what exactly is happening. So we are going to suppose the particle travels from a point A, from A to B in time t. I'm summarizing everything, yeah? So when you find books trying to be more specific, that B is adjacent to A, talking about the angle and everything, in time t through theta. Of course, let me hope people are aware that theta is in radians. So someone tell me, if at all we are saying that the acceleration is centripetal, hence it acts towards the center, what can be the direction of the acceleration in terms of what can be the direction of the acceleration in terms of A and O? So this is circular 2, circular 2, 7. So we are saying that the centripetal acceleration should be acting towards the center. And I'm trying to inquire, if it's really acting towards the center, what can be the direction of the centripetal acceleration in terms of A and O? The direction is AO. That's what I wanted to tell you. I think people can see that AO simply means that we are acting towards the center because our center is O. So it should be A to O, A to O, to O, and O is the center, so it's towards O, like that. Now, very fast, what can be our beginning formula? If at all you get this first formula is what takes us through the derivation. If you don't get it, then you'll be gone. Centripetal acceleration. Centripetal acceleration is equal to the change in velocity. Remember, by centripetal we are meaning towards the center. And towards the center we have chosen AO. You get it? Chosen from our point A to point O. That's what we have chosen. So we are going to look at the change in velocity along AO from A to B over simple as that. So we are traveling from A to B, but because we are considering our centripetal acceleration to be that in the direction A to O, we must respect that consideration or something we are supposing. So respect the A to O. Then as well, we are moving from A to what? To B in a time t. And you all know our time is t, nothing much. So what I want to ask is, what is going to be our change in velocity? Of course, you all know it is velocity over time, that is acceleration. Where does centripetal come in when we say along AO? Because that's towards the center. But that doesn't make you forget that we are moving from A to what? To B. Now, who can tell us what is that change in velocity along AO from A to B? Yeah. You all know that the change will be the final, like it should be the final minus initial. But this time around, we don't have final minus initial. We have velocity at point B and velocity at point A. So someone tell me, what is the change in, okay, what is the velocity at B? What do you take? And what is the velocity at A? Remember, we have two components. Velocity at A has both the horizontal and vertical components. Then the velocity at B is also having the vertical and horizontal components. Which components are we going to really consider? Which components are we really going to consider? Which components are we really going to consider? People are quiet. People are quiet. We have said that the change in velocity means velocity at A minus the velocity at. We are moving from A to B, so the change is B minus A. But I'm asking, the velocities at the different points have horizontal and vertical components. So if you're to get the change, which one is the change? Horizontal components, the vertical components, or the real resultant velocities? With the reason, you see what makes physics hard is you not having a reason behind. Because just like most of you didn't have the reason behind the theta, you could forget, but even when you could cram, there are a lot of angles to cram. You will end up flopping, which is not good. Gladys Gift, why did you put your hand down? I don't know, you've forgotten? Oh, because I said with the reason. Don't fear. Don't use luck in physics. Use the reason that you know. You never know, it may be correct. And I will ask you the same thing when we are deriving the equation for the progressive wave equation. Because it can have sine, it can have cos. But if you're not a good student of trigonometry, and if you're not a good student of, yes, basically basic trig, and of course resolution of forces, because we borrow a lot of ideas from resolving and composing components. Okay. Yes, Gladys. But Gladys, I'm tired of you. You're raising up your hand and you're putting it down. What do you mean?
Good morning, tutor. I think we shall use the resultant.
You see now, Gladys, you've told me the result, and that's why I always want to hear from you first, so that we correct this physics slowly as we progress. You cannot talk of resultant, yet the velocity at A, we said it's only and only having the horizontal component. It has no vertical component. And I'm going to give you now, that is the reason as to why you may not use resultant. So let me hear from AJ. Yes, AJ.
So for me, I'm saying it's vertical components.
Why?
Because acceleration moves in the direction of the velocity.
I want you, good. Proceed. I want you people to listen to his statements.
So the acceleration will lead to increase in velocity and to move in the same direction with the velocity. The velocity will move in the same direction with the acceleration. That's why we have to consider the vertical component, because the particle is moving in the anti-clockwise direction, whereby that's where we are finding the vertical components lying towards the vertical component.
Hey, that is good. You've tried. Well tried. Yes, I've liked his reasoning. Yes, it's like speed is not changing throughout. You get it? And but velocity keeps on what? Changing. But you should also realize that at the different points where we draw the tangents of linear speed and so on and so forth, we always consider perpendicularity. So this is how I want you to understand and recall, because it just told us that we are supposed to use the vertical components. You people, someone can cram and be like, here we use the vertical components. Let me just take that. But there are things you're supposed to appreciate. That as we draw these tangents along the circular path, these tangents are perpendicular to the direction of motion, or the circular motion. And of the horizontal and the vertical components, which component is perpendicular? If at all they ask you that question, that in physics or in mechanics, of horizontal and vertical components, which component is perpendicular to whatever consideration? It's the vertical. That one doesn't need any questions. It is obvious. So because of that relationship, you can understand it basically like that. That we always have what? Tangents along the circular path. And what do tangents mean? Perpendicular to what? To the direction of the circular motion. And of the two components, which components are perpendicular? And then we are like, it's the vertical component. So it's those we shall use. As simple as that. Okay, now, someone tell me, the velocity or the vertical component of velocity at point B is v sine theta. What of the vertical component at A? You write it in the chat. We are deriving. When we get the formula, we are going to just enjoy. What is the vertical component of velocity at point A? It is 0, isn't it? Because at point A, we are realizing that the V is purely what? Horizontal. Yes. So we shall come and say, that the change of velocity along AO from A to B is what? V sine theta, which is the one at A, minus 0, which is the one of B. And we have said we are considering vertical components. Yes, the other thing that can help you recall is this thing. That's why I had to put it here. That the direction of the acceleration is what? AO. That is the consideration in all textbooks. And that's the diagram they used. So when you look at how A to O looks like, it is completely vertical. So why not respect the vertical what? Components? I had to give you the story, but even AO brings it out purely. Yeah. Okay. So v sine theta minus 0 out of the time t. Have it in mind that when you decide to use delta theta, you're supposed to also use here what? Delta t. But it is the same thing. Eh? So that is your choice as a physics student. But since we used the theta and t in the previous lesson, I'm also going to use what? Use that. Now, mathematics. Remember, our theta is a very small angle in radians. Are you aware? Recall that theta is a very small angle in radians. I want you people to get calculators. Get your calculators ready. Theta is a very small angle in radians. Someone may be like, how did you know that it is a small angle yet we don't even know? The mere fact that the physics tells us to have theta in radians, that means it is a very small angle. For you to measure it in degrees, very small angle. It's a very small angle in what? In radians. Get your calculators and put them in radians. Please and please get your calculators and put them in radians. Get your calculators, put them in radians. Get your calculators, put them in radians. Are you ready? Are they ready in radians? Yes. Let's begin. I show you something here. I want you to do for me, just do for me 2 dps. I don't want us to waste time. Okay, 3 dps. But 2 dps are enough. Give me the value of sine 1, 2 dps. You give me the sine of 0.5. You give me the sine of 0.1. Yeah. So what you're seeing, these are the very small angles. I think you people have never seen 1 degree. That's why when the angle is too small, it's better for it to be measured in radians. So this is a very small angle. That's why they always prefer radians. Write for me all those 3 answers. Separate them with commas. The sine of 1, when your calculator is in radians. So you note that the calc is in radians. I want those 3 answers. Separate them with commas. 0.84. This one is 0.84. Then the next 0.48. You can say that this is 1 point. I think this one is the same. I think you can see. However, this last one, I think someone is putting for me 0.0988, but those are 4 dps, and I was interested in only 2 dps. So I don't know if people can realize that this 0.84, it approximates to a 1. Even this 0.48, it approximates to a 0.5, and this one is just coming out. So as the angles become smaller and smaller, provided they are small angles in radians, chances are high that sine theta will be theta. Sine theta will be what? Theta. That's what I wanted you to see. So as these angles get smaller and smaller, smaller and smaller, smaller and smaller, sine theta is always what? The same as theta, as you can see. I don't know if people realize it. The 0.5 is here, but what we are getting after putting sine almost approximate to it. 0.1 is here, but after putting sine, it's like we are even getting the same what? The same answer. Okay. So when I come here, so I've told you to note that for small angles in radians, Never forget that. Small angles in radians, sine theta will always approximate to theta. But I don't know whether people recall where we are. You see where we are? We are at a point of v sine theta minus 0 over t. So v sine theta minus 0 is just v sine theta. So we are still proceeding with our centripetal acceleration A. V sine theta minus 0 is v sine theta over what? Over t. But what have we said about small angles in theta? Sorry, in radians. Sine theta approximates to what? To theta. And then what next? I'm going to come and say, therefore, our A will be V theta over T. Are we together there? Now, people, the math has started. Are we together up to that point? Are we together up to that point? Are we together up to that point? Because we are done. We are done. We are done. Are we together up to that point? Good. Now, I want someone to tell me, those who were so attentive in the previous session, what do you know about theta over t? What do you know about theta over t? Yes, Ben.
Yeah, theta over t, it's omega.
Omega, our angular velocity, not so?
Yes,
Because theta is angular displacement and omega, which is angular velocity, is the rate of change of that angular displacement, isn't it?
yes, sir.
Okay, thank you so much. So, but that one is omega. Hope you write it correctly. So you can come and say, therefore, my A will be V, then here you say theta over what? Over T. So that you substitute your omega very well with no disturbances. So you can proceed after that and be like, your A is V omega, like that. So this is a formula of centripetal acceleration. But remember, we can still come up with other formulae. Not only that. Not only that. So you look here. That is one formula. Hope you people know that this is a V. Let me write it well, like that. Who recalls the formula of velocity? Who recalls the formula of velocity? Yes, Gladys Gift.
The formula of velocity, it is equal
Is equal to what?
to,
Is equal to?
it is equal to radius times the omega, which is the
Yeah, that's it. It's equal to r, which is our radius, times omega, which is our angular velocity. So if you don't forget, after you submit, you mute. That's the problem some of you have. When you speak, you forget. Just do like Gladys Gift has done. Okay, so that is the formula. Someone may be like, I've already forgotten that. How does it even come about? You people, you're not supposed to forget. At least tell me one thing. You recall that circumference is 2 pi r. You recall that. So that we can be like, in case it is not circumference, it can be any displacement. Isn't it? And it's only any displacement. For circumference, that's when we have 2 pi. Of course, you know that 2 pi is 360. So in case it is any displacement, that means it will be any angular displacement. then any R, of course. You get the point? I don't want you to forget these things, please, please. So after that, after having that, you now come and divide by t on both sides. You get the point? Divide by t on both sides. After dividing by t on both sides, you people, this is rate of change of, this is displacement, yeah? Rate of change of displacement is what? Is velocity, and that is our linear velocity. This is rate of change of angular displacement, which is angular velocity omega, then the R. That's how the formula comes about. Yes. Remember, there is no physics logbook. Yeah, so you're supposed to be knowing these things. And you can easily mess up if you don't practice. Okay. So, we know that V is RY, and that formula, from that, you can realize that omega alone is V over what? V over R. You see that? So we are going to do substitutions. I can call this one my equation 1. Yes, very okay. So I come and say from equation 1, I will have my A, then I remove V, I put R omega, then what? Omega. You get the point? So what will be the formula? The formula will be R omega squared. This is our equation 2 for acceleration, of course, centripetal acceleration. And you need to be knowing all of them so that you look at what has been provided and then understand which formula can I really what? Really use. You know that omega is what? V over R, isn't it? Omega is V over R. So I'll come and say, still from the first equation, or you can even just substitute in this one. But from the first equation, you can see, what was it saying? V omega. So you come and say V omega. But what is omega alone? Omega alone is V over R. So you come here and put V over R. And what will I get? My A will be V squared over R. And this will be my equation what? Equation 3. Exactly. And that is the final equation. Final equation. Yeah. Sometimes for omega, people substitute here in equation 2, which is also okay. But me, I just wanted the equation 1. And that's our equation 3. So I don't know whether people are okay with those 3 formulae. Because centripetal force will be obvious if centripetal acceleration has been understood. So are we together there? Weko Saimo, you people, when you are lost, you're supposed to raise up your hand. So where is R? So pardon on that last part. Okay, chances are high that Weko Saimo, you never attended to lesson 1. Because you're asking me, where are you getting R? And that is the only problem in mechanics. When you miss linear motion, you cannot understand vertical motion under the influence of gravity. When you miss those two, you cannot understand projectile. Trust me, if you missed lesson 1, or if you didn't do the work, or if you didn't review it, these things can mean to be disturbing. Yes, because now people are asking me, where are you getting R? Really? R? If you're confused, raise up your hand and ask the question so that I get to know exactly your problem is. Because now we are going for centripetal force, which is obvious. But you must have understood what centripetal acceleration is. Yes, Weko. So I'm not going to answer to any question in the chat. You're supposed to raise up your hand, unmute and speak. Yes, Weko.
Okay, sir, good morning.
Good morning.
Sir, I was lost from where this in question 1, how it came. Yet there we had the A is equal to R into bracket theta out of T.
That is V.
V, eh?
It is V, not R.
Okay.
It is V. Maybe I'm writing it poor. But it is V. Okay, okay, you people, I'm going to be writing my V like this and my R like that.
Okay, sir, thank you.
Okay, my arrow will be like that, then my V, all in all, my V will have a sharp point like that. We also had the concern. I saw Evans, any concern? I think there is no. Okay. Now let's talk about the centripetal force. Yes, Evans.
Good morning, sir.
Morning.
Sir, okay, for me, I came late, but I'm just requesting for the screenshot from an app because I just came
Yeah.
late. Just want to
Okay.
follow.
Yeah. I'm going to show you the screenshot, and I trust you.
Yeah.
Okay. Okay, that was the first one. Are you done?
I'm
Taking it?
done. Yes,
That was the second one. Let me try
I'm
to
done.
finish. Are you done with all the
Yes,
details?
yes,
Then that's the third where you found us.
yes, I'm done.
That is good. So you people, just like the way we talked about centripetal acceleration as that acceleration that is acting towards the center, the same as centripetal force. You should know force. Force was well defined by Newton in his second law. And he told us it is what? The product of the mass and the rate of change of what? Of velocity, which you people call acceleration. So our force is ma, that doesn't change. Then by centripetal, we are simply meaning that force that is trying to act towards the what? Towards the center. So I'll say that it acts towards the center. And by acting towards the center, I all told you that means keeping something in circular motion. Keeps the body in a circular path. Yeah, acting towards the center is what keeps the body in a circular path. And that doesn't remove the fact that the force is ma. Simple as that. But remember, we know what acceleration is. So I'll come and say, but acceleration, we have realized it is either r omega squared or our acceleration, the centripetal acceleration, it is v squared over r. I think now that is better. The v and r, you can distinguish them very well. Now, for force, it will be obvious. So for any given mass of the body m, given that m is mass of the body, what does that imply? That our centripetal force F, so just like any other forces, our centripetal force is going to be denoted by F. Yeah, it's going to be what? Denoted by F in this topic, to mean that. Yeah, there is one of my textbooks that I love most. They show centripetal force as capital F subscript C. Yeah, but for the time physics has been marked, I've been just considering F, provided you're dealing with circular motion. When you say F, it is supposed to be that force that maintains circular motion, which is centripetal force. So F alone is enough. So you come and say, our F will be the M, you get? Then our A, we have said, it is R omega squared. Or our F will be MA, which is V squared R. Like that. You see that? So you'll find them rearranging it in such formats that your F is M omega squared R. So you just know that is centripetal force. So that's centripetal force. So when I use any of these as we calculate, I don't want people to ask me a lot of questions. V squared over R. So those two, centripetal force. Any questions? Any questions? Because now the next thing is calculating. You're going to do some calculations and then we go to the other things I told you. And most of the calculations here resemble. Provided we have this. Yes, Justus.
Yes, good morning, doctor. Like if I'm in an exam and they have told me to look for the centripetal acceleration, then I get it. Then for part B they tell me to get the centripetal force. Am I allowed to continue from where I finished in part A and I just introduce M on both sides of the centripetal acceleration?
I'm not getting what you're asking.
Like for example, we have got the centripetal acceleration. Then if I'm in an exam and I'm doing so, and on part B I'm to get the centripetal force, am I allowed to say but F is equal to MA, so I introduce M on both sides of the formula of centripetal acceleration?
What do you mean M on both sides? I'm not getting that set. I'm getting the beginning part. Are you trying to ask whether you recalculate for A or you just substitute for A? Is it what you're asking?
Yes.
Oh, that is obvious. This is a formula you can use in case they tell you to calculate centripetal force out of the blue. But when they ask you for centripetal acceleration first and then force, then you use MA.
Okay, thank you.
Use MA. Let me put it even here. There I'd put it somewhere up. So from F is equal to MA, you can substitute for A. Yeah. So just use MA. But in case they are telling you to calculate the force at once, that's what you can use. Who is confused? Oh, I think we worked on him. Let me hope Simon is now on the same page with us. Yes, Jovan.
Yes. Good morning, Master.
Mm.
I wanted to inquire from you. What if they ask to get the centripetal acceleration and I use V omega? Is it correct or wrong?
It is also correct.
Okay.
It is also correct just because it is very rare for the same question to give you V omega. Remember, both are kinds of speed. One is linear velocity or speed, the other one is angular. It's just a rare case, but you can use, that's why I gave it as equation 1. But it's just a rare case. Yeah, for the same question to have rads per second and meters per second, it's hard. Okay, I think now we can calculate. Calculations. The part I like most. Yeah, there is a lot of content there is a lot of content that we are going to go through here. I always have this book, you all know it. Yeah, so we shall come here and go through some things. Yeah, shall come and go through some things there. Maybe even before we calculate, we can try to go through them because they are not hard, so that you can ask where you're getting disturbed. Okay, let's go through them because calculations are easy. Acceleration of a rotating object. They are saying any particle has an acceleration whenever its velocity is changing. You know that because acceleration is the rate of change of velocity. So velocity must change for acceleration to be present. You get? Velocity is a vector quantity and may change either in magnitude or in direction or both. Angular acceleration is the rate of change of angular velocity. It is also called the centripetal acceleration or the center seeking because it is acting towards the center. You get that? Do people see that? They are very obvious. So they are saying, explain why a body moving with a constant speed in a circle accelerates. Every time in physics they ask us why something accelerates, just explain why something's velocity is changing. Are you getting it? Because time must move. Remember, acceleration alone is the rate of change of what? Velocity. So when they ask you why is something accelerating, for you just tell us why is its velocity changing, because time must change. It is natural. So you come and tell them why velocity is changing. And how do you write? When a body is moving with a constant speed in a circle, the velocity at any point is in the direction of the tangent at that point. And as the body changes from point to point, the direction of the tangent also changes, hence velocity changes. Since the velocity changes, therefore the body accelerates. The things of the tangents they are talking about. Do you remember the diagram we had? In lesson 1, we drew that circle, and I tried to show you something like this. Those who recall. Are you seeing that the direction of the tangents keep on changing? That's what they mean. That because of that change in the direction of the tangents, that means velocity is changing because it's a vector quantity and change in direction changes it. So a change in velocity simply signifies a change in what? In acceleration. As simple as that. In case you're lost, we agreed, raise up your hand. Or you write it in the chat. Ben or any other person is my chat secretary. They can read it out so that we save time. The formulae, these ones we have looked at them. So they are saying the centripetal acceleration depends on, for you to get to know which factors it really depends on, you look at the formulae. You can look at this formula or this formula. That's why they are telling you it depends on the speed of the body, which is here v, and also the angular velocity omega. It depends on the radius of the circle. You can see r there. It depends on the mass of the body. You all know that force over mass is acceleration. So you like it, it depends on the force and mass. You get? That one shouldn't be hard. Okay. Now, they talked of central forces. And they are saying that a body moving in a circular path accelerates, and we have seen the reason. Therefore, there must be a force acting on it. The moment they talk of Newton's second law, just recall F is equal to what? ma. They try to show you that provided the force is there, the body will accelerate, provided it's having a what? A mass. You get? This force, just like acceleration, is directed towards the center, and towards the center we said it is centripetal. You get it? And we define centripetal together. Yes, Jovan?
You were too fast. I'm not understanding about the central forces. The first statement you made.
That what?
My body is moving in a circular path, accelerates it. They are not understanding it.
It is here. Did you get this question? You read this question. Are you seeing this question?
Yes.
Did you understand it when I was explaining?
I understood.
It is the same thing, don't you see that? Explain why a body moving with a constant speed in a circle accelerates. So it is the same statement. Don't you realize? There they are saying that a body moving in a circular path accelerates. Then there we explained why it accelerates.
Yeah. Okay. Now I'm understanding.
Okay, sir. Now we proceed. We proceed. Things are not hard. They are not. They are saying centripetal force causes a body to deviate from a straight line and continues turning it. You get? Centripetal force, since it's supposed to maintain circular motion, that means it will make the body to deviate from all other kinds of motion. And they are saying so that it remains at a fixed distance from the center. I already said you that the center is our fixed point. And the fixed distance their meaning is radius, isn't it? Because radius is the same from the center up to all points of the circle. Is that hard? Saying centripetal force is perpendicular to the direction of motion. And I don't think that is hard. I don't think that is hard. You look here. We very well know that centripetal force is acting towards the what? The center. Look at all those points. Look at all those points. Don't you see the perpendicularity coming in? That if we are to say that centripetal force is acting towards the center and consider all these directions of motion, the ones we take as tangents, you see perpendicularity coming in. And it's not the first time we are mentioning it. Yes. That's why they are telling it must be perpendicular and acting towards the what? The center. Yeah. That's why they are saying that if that centripetal is absent, then the body will just continue to travel in a what? In a straight line. Because it's there to keep it in circular motion. That's why when you're moving something in a circle and the string breaks, it continues as a tangent and it moves in that straight line until it does what? It falls off. Okay, now from Newton's second law of motion, we derived that and that, of which I also talked about them. So as you also talk about the factors on which centripetal force depends on, you just come. Mass of the body is there, speed is there, v and omega, radius is there, r. And they are not hard. They are not hard. Yeah. So these are just the real life cases of centripetal force, and you need them so much in the new curricula. But they are not hard because we talked of the cases of circular motion and which force keeps circular motion centripetal. So they are more or less the same. You can see they are talking of the planets orbiting around the sun. They are talking of the electrons in an atom orbiting around the nucleus, a racing car around the circular track, a body on a surface on a rotating horizontal disk. This is one of the things we are going to look at today in special cases of calculations. You can see a bead on a smooth circular wire. They are talking of what exactly the centripetal force is. But as I've told you, what the centripetal force does, the centripetal force is always at the center like that. You get it? It's acting toward the center. So that means it can be the force of attraction between this point and this point. You get? So if it is the planets orbiting around the sun, then it could be the centripetal force can be the gravitational force of attraction between the two. You get? Most especially for cars moving around about, it is always the friction. You know, as a drift is being done, that is rotating, you always realize friction in play. So it's that friction that we always do what? Provide the centripetal force needed to keep that body in motion. Hope you people have heard of drifts before. Yes. So remember, the nucleus is positively charged. You know that from chemistry. Remember, the nucleus has two things: protons and what? Neutrons. These neutrons have no charge, but protons have a positive charge. You get? And what is revolving around the nucleus are electrons. Electrons have a negative charge. Protons have a negative charge. Sorry, a positive charge. That means the nucleus is positively charged. So what keeps those electrons rotating or orbiting around the nucleus is what they call the centripetal force, because it is maintaining the circular orbiting of the electrons. And they are telling you that centripetal force is the electrostatic force of attraction. Electrostatic means oppositely, okay, it means the attraction between two oppositely charged dipoles. You know that from electrostatics. I don't know if people are getting me when I say that the centripetal force can be provided by a force of attraction between what is at the center and what is in the circular motion. Or if it is a rod drifting, moving around the circular track roundabout, that friction that you always realize between the tires and the road surface is what provides that centripetal force to keep the car in a drifting motion or in a circular motion. Are we at the same page as far as centripetal force in real life is concerned? Someone is asking for the PDF. I don't have the PDF, but I just have my own book, which I bought years back. So I just take pictures if at all I see parts I may need. But I have so many books. So you people, are we together? Are we together there? Because now this book is done. The parts I wanted, that's all I wanted from this book. Now I think I can go to other books and we do some calculations, isn't it? Yes, Marilyn K.
Good, good afternoon, doctor. About a car moving around about. You say that they are pulled towards the center because of the friction force. How does that come about? Like, how does the friction force pull the car towards the center?
Oh, we are going to see that as we calculate. We have what we call motion of a particle, which particle is on a rotating disk. I think I mentioned that. Yeah, rotating. I'm going to talk about it. We have calculations to do with this, and you're going to see. Let me hope you've heard of what we call normal reaction and everything. So when you reach that point, we shall do calculations and reason everything out. But have it in mind that friction force has a formula. So that formula can help us reach to what you want, and I will explain at the right time. Okay. So here, let me help people recall the other formulae of period and so on, yeah? Frequency and the sort. So that is the derivation of acceleration. You see they derived here everything and came up with our formulae. Whatever they used, we don't care. Okay. A moment. So hope we are at the same page. I've been picking a very important call. So, I think we can now start the calculations. Okay. Let's begin with this question. So here, don't mind all this, but in your free time, you can look through it, provided you're a good student of resolving components, period. Yeah, so example 1. Remember, they are coming up with the same answer. That means we are safe. Okay. Example 1. So this is where we are going to summarize our work from. Where is our workbook? I think it's here. So we are going to read the question, have a summary. Hope people recall what I told them, SK mode of calculating. So they are telling you that a particle moves along a circular path of radius 3 meters. So I'll come and say that radius 3 meters. What else? With an angular velocity of 20. What else? Calculate that's all. Then they want the linear speed. It's always better you first find out what exactly they want for each case, so that you don't calculate an earlier part when you're not aware. So Roman 1, they want you to get the linear speed. So linear speed is V. But this one was a bit obvious. So I told you about the SK mode of calculations. But with physics, in most of the cases, this part is skipped. The one for computation or the evidence of working. It is usually expression you substitute and then the what? The answer. How do we escape computation? We always alter our expression to fit the question, as I told you. So you just come and say, this one is your R, then you make. I told you how. So you substitute V, R is 3 times 20. Then you get your linear speed as 60 meters per second. Then how will they mark? They'll give you a mark for this, mark for substitution, and then the answer. Like that. Period. Then what else do they want? They asked for the angular velocity, but this time around in revolutions per second. You remember what I told you? That when they tell you revolutions per second, don't waste your time. This is frequency. The statement is even here. That angular velocity gives the frequency. So for you, just get frequency. But the question is, which kind of frequency are you going to use depending on what you have? Remember, for you, all you know, now this is supposed to always be your side work in physics. They have asked for angular velocity in what? Revolutions per second. But for you, know revolutions per second, it is frequency. Then you're supposed to recall that frequency is 1 over what? Periodic time. But what did we say about periodic time? We said periodic time is 2 pi over omega. I don't know if people recall this thing. Hey, we derived it together. And I don't want to repeat it. So if you just go back to that session, but maybe I told people that period is time. So it is supposed to be time. And we all know, okay, this is what we say, that time is distance over speed, isn't it? That is the time. It is distance over what? Speed. Then I told people for period, we are completing the whole revolution. Remember, period is the time taken to complete one what? One revolution. And one revolution is circumference, which is 2 pi r. And I remember telling you that the speed we are going to consider, since as we complete the revolution, our speed is uniform or constant. We are not going to cause ourselves issues. We shall use the linear speed, this one. You get R omega, the V. Then that's how we cancelled this R and this R. You get the point? Then we said our T is 2 pi over what? Omega. That was for periodic time. So since frequency is 1 over period, our F would be what? The omega over 2 pi. Why am I doing all this? The question is asking us for what? For frequency. But we have omega, so that means it can hold. Yes, Ben?
So me, I was inquiring about, you said you're going to give us the case 3 of this period. There's another formula that you gave us that we
Yes,
left
I
on.
recall. I recall. That one will come. And when I'm to talk about it, I will tell you. I still recall.
Oh yeah, I was still confused about it, sir.
But you're not going to find it in this topic.
Okay, sir.
So forget it until further notice. Erase it from the mind.
Okay, thank you, sir.
Okay. So Roman 2, so you now know they want frequency. So you come and say that the frequency, as we have realized, is omega over what? 2 pi. So you come and say frequency, my omega is what? 20 over 2 pi. So what is the frequency? After getting the frequency in revolutions per second, you conclude and be like the angular velocity, yes, you want in revolutions per second. You show them. What is the answer, people? What is the answer? I remember telling you how you can press pi. So I expect the answer very fast. I told you may want 4 dps. Okay, today let me use 3. Then you conclude and be like, tell them that what you guys asked are those revolutions per second. So when they ask per minute, because 1 minute has 60 seconds, you multiply that by 60. I've just said that and I've not put it in writing. But you only multiply by 60 if maybe they ask for revolutions per minute. They cannot ask you for per hour, maybe when they are just testing other skills of converting units. So this is what they mark. They will not mark this. Yes. Formula substitution, then the right answer. Hope we are together there. So we go to the third part. Oh, it's 3. Okay. What else do they want? Time for 1 revolution, that is T. Hey, do I really need to do that? Time for 1 revolution, that is periodic time. So since you have frequency, but this is what I advise. Since the frequency is rounded off, don't use it. Use this formula for 2 pi over omega, because you still have the omega untampered with in the question. So this one is a better formula, other than using 1 over f, which f you have rounded off. It is okay, but I'm just giving you the best advice. You say 2 pi out of the omega 20. So what is t? So you people give me the answer, because I now don't trust my calculator. I now don't trust my calculator, so So you have already decided to use 3dp, so you maintain those. If you had used 4 like some of you, so you maintain 4. 0.314. Yeah, seconds, because they're asking for the time period t. And you're done. Then you say that physics is hard, like we are getting marks for doing nothing, totally nothing. Now this question is asking us for the centripetal acceleration. They could even just ask for the centripetal force. So centripetal acceleration, you know the formula. So you just choose which one is going to work for you depending on what you have. There is no logbook. There is no logbook. There is no logbook for physics. You're supposed to be knowing these things. You get? So let's look at what we have. There is this formula of V omega. There is the formula of V squared over R. There is the formula of R omega squared. So which one are we really using? Depending on what we have. You see? We have the linear speed. In Roman 1, we have the omega. We have the radius. Okay, like any can work. So which one would you prefer? Any can work, but which one would you prefer? Someone is choosing V omega. So you can use any, but you're going to realize that the answer is the same. Yeah. So for me, let me choose since the question provided me with R and omega. So for me, I'm going to use the third, because I'm going to use what exactly the question provided. I may not trust my answers. So I'm going to say my acceleration is omega squared R. Acceleration is omega squared R, like that. Yes. So my A, omega squared, and squared R, I think it was a 3, if I'm not mistaken. Then you get the acceleration. Provided you put the right unit. Yeah. So when you use others, you get the same thing. Yeah. When they ask for centripetal force, they should give us mass. But for now, we don't have mass, so we cannot get centripetal force. Yeah. I literally don't see anything hard with these things. Only deriving, maybe. Now, you do that question, all of you. Yeah. You people don't want to do assignments. You do that number and get me the answers, because I know no one has this book. So no one can copy. So you do that number, we go to special cases. You do that number, and I'm giving you only and only a maximum of 5 minutes. So in 3 minutes, you should be done. Provided you follow the SK model. Let me even put it here. So for me, I'm going to just put answers. Let me also do it here. We are going to just check answers. Then you confirm that you've understood, following the fact that you will have passed. Expression, substitute, get me the answer. If there is need of evidence, and you know what the answer should have, you know everything about those letters I explained the other time. Someone is asking, what is SK model? You refer to lesson 1. You people hurry because we have only 1.5 minutes. People, you are using a lot of time. That's not fair because this question is so easy and it cannot exceed 6 marks. So I don't expect you to use more than 6 minutes because we must ensure that every minute we earn. Someone has commented done. Let me expose. You tell me if all have been passed. Yeah. The answer for angular velocity, you can see it is here. 1.26 radians per second. Hope you have that. The velocity, this is the answer. Let me hope you have that. 0.13 meters per second. For acceleration, centripetal acceleration, this is what they have. I hope you have that. And for frequency, this is what they have. But that's not the formula for frequency. So their answer, I think it's not right. I think that is periodic time. Yes. So for frequency, I don't know whether you also have this, but to me it's not right. It is supposed to be omega over 2 pi. Yeah. And the answer will be, what's the answer? Which answer are you guys getting? This is the formula for frequency. Is it right? You people, you used the wrong formula for frequency. It is the same answer. How? Let me check. 2 times 2 to divide by 7, then 1.6 to divide by answer. Hey, it's okay. I've realized it is the same. Okay. But let me hope you used this. So let me hope all of them have been passed. Let me hope all of them have been passed. So you take this as your assignment. Assignment 1. So you're supposed to take a pic, take a screenshot and send it in the group right now. I told you you're supposed to send lesson highlights to your friends. Yes, Ben.
Sam, I would like to inquire how they got the acceleration. Is it correct if you place it in the calculator like that?
Let me check. 1.26 squared times 0.1. Which one did you get? 1.58. What?
Yes.
This is what I'm also getting. Yeah, you're right. Let me check. Did these people do? Squared. Hey people, you are not serious. You're telling me that all passed, yet you have a wrong. This value of acceleration here is not right. But some people are saying past, like, why? Ben, you try using other formula and see, but I think it has to come out. For example, let me see. Do we have our linear speed? Yes, our linear speed is there. Let me see. What if someone says 0.13 times 1.26? Yeah, the answer is okay. The answer is okay. You can have different answers. Yeah, you can have different answers because when you try to use acceleration as linear speed and angular velocity, you're going to get 0.1638. Then when you try to use v squared let me see, the V is 0.13. When you square it, now when you use the A being V squared over R, then you get this answer. So this answer is okay for this formula, you get. Then for this one, you get something different. Then for this formula, you know what you get? You get a different answer. But this is what I had devised. Since the question gave us radius R, you get, and the very first thing we got was angular velocity, then we got speed. Maybe you can use the one of, which one can we use? Which one can we use? Because we got V from angular. So that means anyway, they will accompany for both. You just need to use those values that you think have the least error. Because V came from omega. And all formulas have V, unfortunately. Those without V, they have omega. So that means the best formula to use is actually this one, Roman 3. Because we got omega first and radius was already in the question. So that answer of 0.15 something is the best answer. This other formula with V came from omega. They are right, but the other one is the best. Hope you understand. Okay. Now, before we go through this work, let's first see where exactly. I think here. So even here they talked of the derivation of V squared over R, like that. They got our answers. They also talked about centripetal force. I think you can see here. So this is what I was asking. I don't know who asked. I think it was Justus. I think you can see Justus here. They asked directly the magnitude of force. So you need to understand that the 2 kilograms was our mass already in kilograms. The angular speed of rads per second. We had the omega. Then the radius. We had it 10 centimeters, which we are supposed to convert to 0.1 meters. And that is our radius. So we have R, we have omega, we have M. That means the formula to use, you do your side work, and then realize that it is this formula that will work. You get? Without you first getting acceleration and then force later, it is wasting time. It is wasting time. So that is it. The formula, the substitution, and the answer. But I advise, since you always use answer sheets, you have the expression alone, substitution alone, the computation if necessary, then the answer, and you know what the answer should have. Someone was asking what's the SK model. You will understand everything. So these are other trial questions. You people, it is easy to get centripetal force because I've taught you how to get acceleration. So we even have answers here. So this is assignment 2. So you also take the screenshot and post in the group as highlights. Any number that fails to come out, you post in the group and maybe members can help. We are there. So you all know the vertical circle is out of these things. Yeah. Then after the vertical circle, I think the next thing shall be the conical pendulum. So vertical circle, ignore. I told you the conical pendulum, it will have a special lesson. Yeah, because it has some serious physics. To be so specific. So we are also done with this document. I told you for now I'm using so many documents so that we can collect knowledge from all corners as you organize things in your OneNotes. Yeah. Done. So we are done with that document. We are now on this. We got done with the other one. So we are on this document now. Isn't it? As we use our workbook slowly. So we are here. Okay. So I want to tell you something. I don't know whether you people know these things. I don't know. When we are still in kindergarten, there used to be those swings that used to move us in a circular path. You know those things? Of course, they also had a fixed point somewhere here in the center. They used to keep us in that circular path those days. So, as speed increased, you realized you used to feel a certain force that pushes you outside. I don't know if people understand. Do you recall that force? That used to, as if it is pushing you outwards of the circular motion. Do you recall it? When you're moving in a circular path, when you're rotating, there is that force you used to feel, and it's as if pulling you outside of the circular motion, outside of the circular motion. So that pseudo force, in physics they call it a pseudo force. Yeah, it's a pseudo force because it is just a feeling. Pseudo force. So it's like you're feeling it, but it's not actually there. It's a pseudo force, and that's what they call the centrifugal force. So because it is outward, it has unequal but opposite, which is acting towards the center, and that is the centripetal, which I've already talked about. You understand? The other one is outward, which you feel first. That's why they call it the initial outward, because you actually feel it. But then there is what they call the equal and opposite, which is acting inward, and that's the centrifugal. Sorry, the centripetal, the one that keeps us in the circular motion. The other one is the pseudo force, the centrifugal. Pseudo force, centrifugal. Simple as that. So they are telling you that they are telling you content on the centrifugal force, but since it is a pseudo force, even the content is pseudo. So it shouldn't stress you as of now. That's why the syllabus is very clear. Talk about centripetal. So they are telling you that that force that counterbalances the other funny one is the centripetal, and it is always acted towards the what? The center. The definition of centripetal, we have oversaid it. I don't want to repeat. And you can see the formulae is there. Yeah. All these explanations, they will make sense when you read through. They are asking why there must be a force acting on a particle which is moving with uniform speed in a circular path. I talked about that. That's because you may not read it. This is what I had said. The explanation we had at first, it was talking of why something moving in a circular path with uniform speed accelerates. We explained it and you understood. Now here they're asking for why there must be a force. But you all recall that force is what? MA. That means if there is acceleration, there is a force. You get? So the question that we did at first, it was saying, why is it that if a body is moving with uniform speed in a circular path, it is said to be accelerating? Now here they are saying, for such a similar body, why should we say that there is a force acting on it? But force is MA, so it is the same what? Explanation. Just don't need to complicate physics. So these are examples of the centripetal force in real life that we talked about. You can just read through and see maybe whether the literature is different. Yeah. Someone asked me to put these books on the drive, and I'm going to find ways of doing that. You just need to remind me. I think you can. So this was talked about the gravitational force on planets, the electrostatic force on electrons. Don't ignore examples to do with the vertical circle, conical pendulum, we shall see that. A moving car, we saw that. So all these, we try to do something about them. You can also see a car moving around a circular track. You can see the friction force that I told you about that provides the necessary centripetal force. So if you've been listening to me, when you read this, you'll understand. Problems will come when you want to read things after a very long time. Actually, let me give you a chance. You take a screenshot. For the other definitions, they are the same things. But you take that screenshot, maybe you can read later on, and you'll understand if you've been listening. If you've been listening, you'll understand. Okay. So you can see here the next thing, it is a vertical circle. But you know, vertical cycle or circle is out of, is not our thing. Don't need it. So this is what I was telling you. That in most of the cases, they combine motion in a horizontal circle with the conical pendulum. I don't know if we should also do the same, but I prefer handling this later on. So I'm going to first give you the basics of the horizontal circle today, because it's not hard. But you should get your pens and books ready, because I'm going to dictate some work. Yes, I'm going to dictate some work. The next time we shall just handle the complex horizontal circle, which is the conical pendulum. Yeah. But for today, we are going to talk about the basics. The basics of the simplest horizontal circle. Okay. So people have taken pictures of the assignments. So it should be people who are good listeners. Why? Because as I've said, there are things I'm going to just dictate. I don't want to copy questions. So I'm going to be reading questions, we summarize them together. First, we are going to just have what I may call an introduction. And after that introduction, from here, I will begin straight away with calculations. Of course, there is nothing much here to derive because most of it has been said. So you just need to listen. I'm going to do one part, which is a particle on a string. Then my research for today, I've not given you any research yet. It's going to be on motion on a rotating disk. You can't read, you understand, but I'll give you the hints to follow. So that next time, I straight away go to the conical pendulum. So what do I mean by motion in a horizontal circle? So you all know we talked of our circular path where of a constant acceleration with its magnitude. Now, there are things you're supposed to understand. Let me first draw some diagram here. So this is what I want you people to assume. But please have it in mind that here we are breaking down concepts. After, you're supposed to go and read the notes. If you have listened to the concepts, the notes will be very easy. You get? Okay. So this is a smooth horizontal surface. Like that. So assuming we have our fixed point here, and then we start to have our body trying to move in a circular path. So this time around, allow me draw something a bit spherical, so that we can have enough space for showing all what we want to show. So I'm going to draw something spherical, like that. So this is our fixed point, and this is the smooth horizontal surface. By smooth, I mean there is no friction, and it's moving in such a direction. Now you all know from there up to that point is our radius, isn't it? Remember, someone may be like, but what are you really doing? If this is our fixed point, assume that we are having a string, and this is our body at this instant. This is the body. So assuming that this is the string, assume that this is the string like that. That one is our string, and this is the fixed point. So this is where we are aiming, and we are trying to move it around like that, like that. So don't mind the spherical shape, it is just 2D. Yeah, but you know that in 3D, our motion is circular. Okay, now, there are things you're supposed to know. Remember, this body is resting on a smooth horizontal surface. You know that people are really imagining what I'm really trying to show them. This is a smooth horizontal table. And I got my point, my center where I'm going to aim. I got a string, I tied my body. You get? So this thing is my body. Let me put it here and say body like that. So that is my body, and it's what I'm moving around. That is my string between the center and the body. So I'm moving it around. But when that body is just seated on the table, when it's just seated on the table, it exerts its own weight onto the table. And the weight of that body, you all know, it is always what? mg. But remember, every time anything is sitting on a table and it exerts its weight mg, the table responds by reacting, or the body reacts by exerting the same force onto that body. And that force is what they call normal reaction. And normal reaction is denoted with letter R. That is something you know even from O level. So I will come and show it like that. And I put R. Are people getting it? This body is sitting on a table, which is smooth, no friction. When it sits on it, it exerts a force equal to its own weight onto the table. Then the table reacts by exerting unequal but opposite force onto the body, which force we call the normal reaction, R. I don't know if we are together. Then something you're not supposed to forget, that this body is moving, or this body is rotating. And you know, as it rotates, it covers a certain angular displacement, what? Theta. And the rate of change of that angular displacement is what they call angular velocity, omega. So it's moving with that angular velocity, omega. That's why my arrow is curved to show rotation. Simple as that. So our O is always the center, and you know that that is our R. I'm not repeating that. So I don't know whether people are okay with that diagram. Before I put the most important statement, where should I put the most important statement? People look at that diagram before I put my important statement, as I see where I can put it, because I don't think you can advise me well. You know, I've seen. Okay, now people, we are having a string. Which string is the one onto which the body is suspended? And it's that string trying to move the body around. Remember, the strings in physics have a certain force within them that enables them to hold bodies. Which name is given to that force? The force in strings. Which force enables these strings to hold bodies? Who can tell me the name of that force? You write it in the chat. The force that is present in strings that enables these strings to hold bodies. It's called tension or the tension of force. Now my question is, where is this tension going to look? Where is this tension of force going to look? Is it going to look towards the center? Is it facing towards the center or away from the center? Towards, away. Of those two arrows, which one is correct? You tell me. Towards the center, away from the center. Towards the center, away from the center. Towards the center, away from the center. Towards, we've been talking about that. If you're talking about away, you've not been following. Because we said for you to have the body kept in circular motion, whatever is acting should do its level best and make sure it looks into the center. That is it. That is it. So our tension in this string should be like that, and I'll give it the letter T. So I want you people to be careful. We have R there, we have MG there, we are having T there, we are having R there, we are having omega there. So you should follow. The letters are many. Yes, and we are going to come up with the formula we are going to use for today. Now I want to ask people. How can I get centripetal force from this? You look at whatever is on the screen and tell me, how can I obtain centripetal force? Oh, if I may ask, of all the letters on the screen, which letter is the same as centripetal force, or which letter is going to give us centripetal force? Someone is like, wait for me the tension concept. I've said tension is the force in strings that enables them to hold bodies. So every time a string is holding a body, this body is stretching the string. And every time you're stretching a string, it experiences tensional force. I think you know that tension force is what if at all you're pulling a body apart, every time you're stretching a body, it experiences tension or tensional force. So when a string is holding a body, it is stretched, hence it will experience tension. And because we are dealing with circular motion, which must be kept or maintained, our tension should act towards the center, just like centripetal acceleration and centripetal force. And I'm asking, of all the letters we are having on the screen, which letter do you think will provide the centripetal force? Is it the MG? Is it the R? Is it the T? So just like the things we've been talking about, the examples of tensional force in real life. Yes, I've told you that since it is the attraction between the two, between what is at the center and what is actually moving circularly, the attraction between the two will always provide the centripetal force needed to maintain the circular motion. We talked of electrons around the nucleus. We talked of planets around the sun. We talked of a lot of things. And this time round, we are talking of our body around our center we've chosen. So that tension between the string, the tension in that string, the tension in that string is what will provide the necessary centripetal force to maintain the circular motion. So our T provides the necessary centripetal force to maintain the circular motion. And that is all. So when I come here, we shall now begin resolving, and then we shall say resolving vertically. This one is the easiest. For physics is not hard. You make sure you just understand the concepts. Resolving vertically, our R will be M key, you get? Then resolving horizontally, resolving horizontally, resolving horizontally. You can see that our tension will be the centripetal force. And what do I mean here? Centripetal. I told you that already. That in this topic, when they write F, even if they don't tell you, have it in mind that it is the centripetal force. Centripetal force, yeah. So you know the formula of centripetal force, eh? So we shall just come here and say, therefore, our tension will be M V squared over R. Of course, the body that is moving has a mass. Yeah. Or you can take on this M omega squared R like that. And you're done. So all calculations we are going to be doing, they're going to be rotating around there. That's why I want people to do the first example on your own. I'm not the one who is going to do it. I just want you to do that. I just want you to do the examples, the first one, on your own. It's not me who is going to do them. Are you ready for the first example? I told you I'm going to just dictate. We make a summary, and then hey boy, let me first give you this note so that when you come across it, you don't be surprised. If I'm having my circular motion like that, this is my center, you get? I have this thing of towards the center, and I have my thing like that, which is tangential. This is tangentially. Then this is radial. You know that radial means towards the center. So people, am I right to say Am I right to say that centripetal acceleration I've forgotten the textbook. Centripetal acceleration is radial but non-tangential. Is that statement right? Centripetal acceleration A is radial but non-tangential. Is it right? I've forgotten the textbook, but I think it's Tom Duncan. So when you find that statement, I don't want it to over-confuse you. Even when you find it in a calculation, please you reason it out very well. Yeah, you all know centripetal acceleration acts toward the center, so it's radial, but non-tangential. Hope that is obvious. So if I want you to listen to this number, we are going to summarize it together. Then it's you people to do the calculation. I want you to listen. It is question 1. So assume we read it together. They are saying that one end of a light inelastic string of length 1 meter, one end of a light inelastic string of length 1 meter. Are you listening? So they are telling us the natural length is 1 meter for that string. You know, we have been talking about the string, hope you know, is fixed to a point O on a smooth horizontal table. A particle P of mass 2 kilograms, a particle P of mass 2 kilograms is attached to the other end of the string, is given a blow which sets it in moving in a circle of a plane. I think people can understand. It's given a blow, then it starts moving in a circle on a plane with a constant angular velocity. They're giving us angular velocity of what? 5 rads per second. So let me hope people have listened to that question. The question was saying one end of a light inelastic string of length 1 meter is fixed to a point O on a smooth horizontal table. A particle P of mass 2 kilograms attached to the other end of the string is given a blow which sets it moving in a circle on a plane with constant angular velocity of 5 rad per second. They are like, find the, before you even go to other things, let's first sketch. So how do you realize you're dealing with motion in a horizontal circle? Then when they mention smooth horizontal table, so you come and draw the smooth horizontal table. You know that. So we shall come. Someone may be like, but why are they really giving us the length of the string? If I want you to look at that diagram, do you realize that radius r is the same as the length of the string? Who can see that? Do you see that the radius is the natural length of the string? In physics, they usually call it natural length, but they can just say length in the question. Do you people see that? That radius is equal to natural length of the string L? Who is seeing that? What people need me to illustrate? The string is coming from there up to here. That's the natural length of the string L. But you can also see the radius. It is almost the same thing. It is from the center to the periphery of the circular motion. So have that in mind, yeah? That the radius is the natural length of the string L. So when it's not given, don't complain. So what are they saying? They are saying that one end of the string of length is fixed to a point O. So this is the point O is fixed to a point O on a smooth horizontal table. So the horizontal table, our particle may be somewhere here. So a particle P of mass 2 kilograms is attached to the other end and then given a blow which sets it moving in a circle. So our circle will be this, as you know. So they are saying the particle P may be somewhere here, as usual. You see that? And then we know just because I'm drawing a very big particle, but hope you people understand, yeah? The particles are usually very small, so I don't want you to assume it's over-exaggerated as I'm exaggerating it. So we're having our center here. So you also have our particle here, particle P. Just try to make it a bit larger. Like that. So they are saying our center is O. They are saying our particle is P. Are you following? Then they are saying, listen, one end of a light inelastic string of length 1 meter. So this is 1 meter. So I come here and show 1 meter. We proceed. Is fixed to a point O, which is here point O, our center. On a smooth horizontal table, you can see the table, the parallelogram. A particle P, you can see where P is, that's the particle of mass 2 kilograms. So because of 2 kilograms, I'll come here and say mg. But remember, m is 2 here. So it's better I say 2 g. This is 2 g. Any of that per getting me. They are saying the mass is 2 kilograms, and thank God it is already in 2. It's already in kilograms. And you all know that weight is mg. You get? And where m is mass in kilograms. So my weight can just be 2 g. Hope you're not seeing that for the first time. It is something so common in the subject. So you know that that is the weight the particle P is exerting onto the table. So the table will react by exerting an equal but opposite force onto the particle, which is called the normal reaction R. So come here and say this is R, like that. Hope you're following. Then we all know that there is always tension in the string they are using. But before we even go to the tension, what are they saying? A particle P of mass 2 kilograms attached to the other end of the string is given a blow which sets it moving in a circle. We have seen the circle with a constant angular velocity of 5 rad. So they are telling you that the what? The angular velocity is constant. That means I'm free to come and show it. I'm free to come and show it like that. I told you for angular, use a curved line. We shall see for linear that we use what? We use the other one, which is straight. So you come and show angular velocity. They said it is 5 rad per second. Yeah. So just come here and be like, this one is 5 rad per second, like that. Then you start calculating. So that is the sketch. But remember, they are going to ask you for things like tension and so on and so forth. So you can come here and say, our tension will look there, and it's what will provide the centripetal force. On top of that, you can even come and show your radius. Remember, you already know it's 1, but you come there and show that my radius is 1 meters. SI unit meters. And after that, I believe you're good to go. You're good to go, that is enough. Don't show other things. These things of coming and you show the vertical plane, they may be important or not. It's not necessary. Even those who always want to come and complete the what? The horizontal plane. But remember, it's only a few cases in physics where the sketches are marked. Only a few cases where they realize it's actually worth it. But there is when they are not needed. But as you're sketching, do what you can, provided you use a ruler. If you don't use a ruler, you face it rough. Hope we are together there, people. Now, someone tell me, this is the first question. The first question they asked You listen. Find the force exerted on P by the table. So you're supposed to write, if you really want it. Those who will be listening to this in the future, you write the question. It is not anywhere. It is in my book, but I've not yet made my book official because I want to first include scenarios. Then I release all my books for all subjects. It's so that you enjoy. So Roman 1, they're asking for the force exerted on P by the table. Are you listening? Force exerted on P by the table. What do they want? What do they want and what is the answer? Tell me what they want, then you put a comma, and then you include the answer. You people, you're giving me wrong answers. All of you are using, it's only one student who has used the 9.81. People, this is physics. This is physics. This is physics, please, not mathematics. So you're not supposed to use 9.8. You're supposed to use 9.81. Okay. So R is what they want. Someone called it resultant, but I called the normal reaction. Maybe I should write it because I may assume people know it, yet they don't. Friends, this is called normal reaction, not resultant. Resultant does not exist in physics. The word resultant alone does not exist in physics. It's either resultant force, which is Fr, resultant velocity, which is Vr, and other resultants. This is normal reaction. You're supposed to come and say normal reaction is mg. That is, of course, after resolving vertically. Then you come and say our mass is 2 kilograms. Our G is 9.81. Yeah. And then we get our R as the 19.62 newtons. That is the force. The table exerts onto P and get your max. Get your max. Free max. They're asking for the tension in the string. Someone tell me. Do you people realize that provided we derive our formulae well and we have very good introduction, these calculations can be obvious, provided you know how they flow. Now, Roman 2, they're asking for the tension in string. Let me even help you put the questions here as you calculate for me tension. People, get for me tension. This is the force exerted by P. The Roman 2, tension in the string. Yeah. The problem, some of you are just writing me answers. You're not showing me your steps, which is very bad. People are getting tension as what? People are getting tension as 50. Seems people knew these things before. So, it depends on what you're going to use. There is this formula for A. There is this formula for A because mass is obvious. There's also this formula for A. So regarding what I have, I don't have V, but I have angular what? I have angular velocity. So I'll use the other formula that has R omega squared. So I just come and state the formula. Come and say my T is what? Is M omega squared R. Then I come and substitute. My M is 2. My omega from the question is 5 squared. Why don't I use times? Some of you come and put there 25. You will fail. Put 5 squared, not 25. My radius is 1. So I get my tension, which is also a force in newtons. Yeah. Mm. Mm. And then you say that is hard. For this question, you're going to do it on your own. But let me tell you, all questions are like this. All of them. All of them. So the next one is yours. The next one is yours. And it's not hard. And it's not hard. It's not hard. It's not hard. It's not hard. So be strong. So question 2. One end of a light inelastic string of length 2.4 meters. You people, you should always note the word inelastic. There is when they tell you that this string is elastic. Let me see those people who have not studied elasticity yet. Let me see those people who have not studied elasticity yet in the chat. If you've not yet studied elasticity, that is Hooke's law of elasticity. If you've not studied Hooke's law, you say me. If you've not studied it, I see people more than 5. Hey, you're many. That means I'm not going to overtalk it, right? Let me see. Yeah, people about 10. Okay. It's okay. The time we shall perfect. Don't worry. Okay, now they are saying a light inelastic string of length 2.4 meters is fixed to a point O on a smooth horizontal table. A particle P of mass 1.4 kilograms. (1.5 kilograms) attached to the other end of the string is given a blow which sets it moving in a circle on the plane with constant speed of 4 meters per second. You people, is this speed angular or linear? They are saying constant speed of 4 meters per second. Which speed is it? With the reason, raise up your hand. Raise up your hand. Don't type in the chat. The first question we did, they told us constant angular speed. So they gave us the angular. They said angular. But here they are not saying like anything like angular or linear. They are saying constant speed of 4 meters per second. So which speed is it and why? Okay, you can text in the chat, but I prefer someone raising up their hand. Constant speed of 4 meters per second. Yes.
Yes, good afternoon, Doctor. it is linear speed
Why?
because the speed they are saying it is constant, it is not changing.
Even in the first question, they said constant angular. There's another reason I want. Yes, life.
Okay, I think that is V. Reason being, when you
It
look
is
at
what? It is what?
that V, not omega, by considering the units that are given. If it was
Exactly, the unit.
omega, yeah.
If it was omega, they would tell us radians per second, isn't it?
Yes.
So you can mute. Thank you. So that is V, meters per second. And they say meters per second, you know what to do. Rad per second, you know what to do. Yeah, that's it. So you people, the first question that they want, I want you to follow ESCA model. They want Roman 1, the force exerted on P by the table. These are just basics of the horizontal circle, motion in the horizontal circle. Then Roman 2, they want the tension in the string, which is equal to the centripetal force. So I'm waiting for answers. I'm waiting for answers. You people don't want to do assignments, so we shall be doing them from here. We shall be doing them from here because you don't want to do work. There is another number waiting for you, very serious. That is question 3. Hey, paper fast, paper fast. Paper fast, paper fast. People are very fast, and I think I'm seeing people getting the same answer. Seeing people getting the same answer. which is nice. So here what they want is R. Here what they want is R, which is mg. So you proceed below. Then the tension, since they have given us V, hope people have used mv squared over R. And you know that R is our natural length of the string. And I think people have used that. So assignment. So assignment, this time round, I'm going to dictate. I told you to get your books and pen ready. The problem, if I share my book, most of you are going to ask me for that book. And I'm not ready to give it to you, not until I put scenarios. Okay, now, number one. I'm going to help you interpret it. So you just listen to the number. They are saying one end of a light inelastic string of length L. So yeah, they said length L. They didn't provide the length. Are you following? Is fixed to a point O on a smooth horizontal table. A particle P of mass 8 kilograms. So the mass is 8 kilograms. Because I believe all of you can make a summary. Attached to the other end of the string is given a blow which sets it moving in a circle on the plane with constant speed, 5 meters per second. So that is speed, that is V meters per second. Hope you're listening. If the tension in the string is 25 newtons, so they are giving us the tension in the string this time round, telling us the tension in the string T is 25 newtons. They're asking us Roman 1. Find the force exerted on P by the table, so they want R. So they want R. Then Roman 2, what are they asking? They're asking for the value of L. Yeah, value of L. So that is number 1. Number 2, they're saying a body of mass m kilograms. So this time round, the m wasn't provided, but they said it is m kilograms. Lies on a smooth horizontal surface and is connected to a point O on the surface by a light inelastic string of natural length 50 centimeters. So they gave us natural length 50 centimeters. What are they saying? What are they saying? They're giving us tension 28 newtons. Then they're giving us still constant speed. So they are giving us the constant angular speed of 7 radians per second. Then the question is find the mass. Because I believe all of you can make a summary. Yeah, so hope you also post that assignment in the group. Hope you're done. Then note for calculations involving an elastic string shall be covered after Hooke's law of elasticity, that is under mechanical properties of matter, where elasticity is part. Yeah. So when you cover Hooke's law of elasticity and talk about the elastic string, now we can also come here and talk about the elastic one. Yeah. So those who will be listening to this in the future, you will have to look for where we covered Hooke's law from. Then you will now come back to further lessons of circular motion and see those ones that involve the elastic string. Simple as that. Then the other research of mine, now the syllabus never specified that we should actually give you the calculations concerning a particle on a rotating disk. Research about a particle on a rotating disk. Particle on a rotating disk. But have it in mind, note, it can only be understood after friction. It can only be understood after a branch of solid friction called static friction. Can only be understood after static friction. So if you don't know static friction, don't even bother. But the syllabus book didn't specify that we talk about it, so I'm just giving it to you as research. But trust me, when you study static friction, then those calculations, of course I'm talking of calculations on that particle. Calculations on that particle which is on a rotating disk. But you can only understand it after what? Static friction. If you don't understand static friction, then you cannot get it. You cannot get it. Why I've really skipped the part of the elastic string, because it has things like the Young's modulus. Yes, the Young's modulus, what? Lambda. It has the L and X. So that means we shall be bringing in R. But if at all you're well conversant with Hooke's law of elasticity, you can look for those calculations, because now you just combine with the knowledge you've gotten today and you will calculate. If you're also that student who is well conversant with static friction, when you go and cover this thing on a rotating disk, you'll understand, because they will tell you that the friction is what will provide the centripetal force in case that particle is to slide over the what? The rotating disk. You get? So that's my advice. If you understand static friction, go ahead and research. It will be very obvious. If you understand Hooke's law of elasticity, you can research. But I cannot just waste time to cover them right now. Yet, we have not covered Hooke's law of elasticity in details, and we have not covered static friction in details. But those who are all conversant with those ones, I've given you a go ahead. So the next time I appear here, we shall be dealing with the what? The conical pendulum. So you do those numbers and post them in the discussion group, but even when I tell you, you don't usually do that. So next time we are covering the conical pendulum. I don't know when we are next meeting as far as circular motion is concerned, but in case I put an abrupt lesson, please comply. But next time we are introducing waves. Yeah, we shall move slowly. This is just week 3. We have up to week 8. So don't worry. Science Scholars Academy based in Uganda. This is my personal number if you want to talk to me. Personally. And in case I didn't respond, WhatsApp calls. Yeah. So our next stop, I've said, is the conical pendulum. The complex motion in the horizontal circle. Yeah. So I'll get back to the syllabus book and be like, bye-bye. Bye-bye, centripetal force. Yeah. The next thing, the conical pendulum. And I want us to do it this week. It's not hard and it's not much. And you should remind me at least if you can. We can fix 2 hours on Sunday and we do it. So the physics coordinator, by the time you listen to this, or anyone who is concerned as a physics student, let us fix time on Sunday after we have covered a good percentage of waves. We also do the conical pendulum. It's not so big. It's not so big, but endeavor to do work so that you're not disturbed by the content that gets much and much and much with time. Yeah. And those who have managed to stay on up to this time, I appreciate. Okay. That is it. People want to take screenshots. I don't know where you last took. I think this is what we last took. You take that one. You take that one. You take that one. Take that one. Take that one. Take that one. That's our next stop. I sign out. Okay. People, thanks for attending. We meet. Bye-bye.